Paper 5 long. An explanation of the Marlow's networks of expectations. Suppose we classify people according to two criteria: be tall, A, and be handsome, B. If we use this criterion dichotomically, we obtain four types of people. Each of these types of people is a theoretical object. A theoretical object is a unique and distinct set of qualities. The number of objects in a network of expectations depends on the number of criteria, as well as the degree of being in which we divide those criteria. In this case, we only distinguish handsome and ugly, but from nothing handsome to very handsome, the number of types could be infinite in theory. Starting from the common qualities of objects, we can build sets. In this case, the objects above share the quality A, tall. The objects below share the quality not A, short. With the common qualities, we generate the OR nodes. First, we have the OR node A. Second, we have the OR node not A. Nodes A and not A depend on the same criteria in common. We represent the criteria by underlining the variable. The OR node A will be true if there is someone tall, handsome, or ugly. The OR node not A will be true if there is someone short, handsome, or ugly. The criterion node will be true when there is someone tall or short, ugly, or handsome. From the nodes of the object, we can also generate AND nodes. When there is someone tall and handsome and someone tall and ugly, the node AND A is true. When there is someone short and handsome and someone short and ugly, the node AND node A is true. When there are all kinds of people, AND supernode is true. So, starting from the objects, we build sets that go from the OR nodes to the AND nodes. Sets can be built from the perspective of any criteria, which does not affect object nodes. The set is the basis of the inference, regardless of the number of variables of the number of divisions in the criteria. We call the set of all sets alpha.
We can consider all the nodes of the network initially uncertain, with the numerical value equal to 0 or chromatic equal to yellow. The color codes have an exact translation into numerical codes ranging from -1, sure that it is not, going through 0, uncertain, to 1, sure that the presence is true here and now. To understand the laws of the spread of certainty, we can assume that we are talking about the set formed by my two twin cousins John and Peter. The OR node will be true when any of them is present. The central nodes represent the specific individuals Peter and John. The upper central node will be true when it is certain that John is here and now. The lower center node will be true when it is certain that Peter is here and now. The end node will be true when it is certain that both are here and now. In case number 1, the starting point of the inference is the affirmation of the OR node, that is, we say that it is certain that there is at least one object. It could be the case, if in the distance we see one of the twins entering our house, but without being able to say if it is Peter or John, and without knowing if the other is inside or not. At that time, we have sufficient reason to think that there is a twin in our house. The OR certainty is divided between central objects, so that the OR value is divided equally between John and Peter. At the same time, the AND node acquires a truth value equal to the average truth of the central nodes, in this case equal to 0.5. We still have reason to think that it is likely that the two twins are in our house here and now. In case 2, we begin by affirming a central node or specific object. For example, we see John entering the house, but without knowing if Peter is inside. From there, We deduce that it is true there is someone, and we deduce that the weight of the certainty that it is true that everyone is there, and, is equal to 0.5, which is the average of 1 and 0. In case 3, a source of confidence assures us that all twins are at our home. Then we know that John is in our house here and now, and we know that Peter is also in our house. We also know that it is true that there is at least one, or what is the same, we can assure that the inclusive disjunction Peter or John are at home is true. In case 4, a source of trust assures us that it is false that there is someone. Then we can infer that the central nodes are false and, consequently, that the end node is false. In case 5, the only information we have is that we have seen John leave our house, but not knowing if Peter is inside. At thesis time it is true that the upper central node representing John is in our house is false, consequently, it is false that both twins are at home. The central node representing Peter remains uncertain. For its part, the OR node acquires a value of -0.5 equals orange, which is interpreted as likely to be false, and which results from averaging the false value of the central nodes of the object. If we think about it, the only certain information we have in case 5 is that John is not there. Is there anyone there? Probably not, and although Peter can finally be in our house, at this moment, the information we have inclines us to think that he is not. In case 6, we are assuming that the proposition everything is true is false. At that time, we only know that both twins are not at home. So, we have the same reasons to think that it is true that probably he is not at home for each of them. That is, we have -0.5 against the presence of one and -0.5 against the presence of the other. At the same time, since we only have evidence to think that one is absent, we only have reasons to consider the OR node as probably false, which results from averaging the falsity of objects. Statistical reasoning in the second inference. Imagine we asked 10 young people if they know who Eva Peron was. If 9 of them already answered no, we can conclude that the 10th young man probably does not know her either. How have we come to this conclusion? When we give the object nodes a non-zero value, the values of OR node and the values of AND node are also modified as a result of what we will call first inference. Based on the network propagation rules we set out above, we can make a second inference to update the value of all object nodes taking into account the values acquired by the AND and OR nodes. In any case, we believe that it is convenient to distinguish the expectation that the 10th young man does not know Eva Peron from the values obtained in the rest of the occasions by direct evidence. This expectation value seems more theoretical, more mental, and that is why we will represent it bordering the nucleus of the node. In this way, we can separate what we know from what we assume. We can try a classification of the types of reasoning that occur in networks based on the strength of the inference. The deduction propagates logic values of absolute certainty. In induction, absolute values are only reached when all the values of the object nodes are known. In probable reasoning, the values are only approximate. Finally, in the statistical reasoning generated in the second inference, the value of the object node is only supported by direct evidence from the rest of the nodes of the set. Following the tradition of mathematical logic, except to the conjunction, we define the logical connectors by the combinations they eliminate from the network. A node can be eliminated when it is unreasonable to expect that there is some stimulus with those qualities. The elimination of a node implies the elimination of all the nodes that depend on it. The object nodes removed are not taken into account when considering the values of AND nodes and OR nodes. Of course, We don't need that much information to solve Chrysippus's Indemonstrables or propositional calculus exercises. To solve propositional calculus we don't need AND nodes. In 2017 we created a simpler version of the networks in which the logical connectives are represented by eliminating certain nodes from the network. The network numbers indicate which premises eliminate the black nodes. We reach conclusions by following the rules of inference of the expectation network. Networks can assume the conventions of mathematical logic or Aristotelian logic regarding the affirmation of existence in universal propositions. If we consider a term hypothetically, we maintain the zero value of its node. If we consider that the presence or the absence of a node is true here and now, we give it a value of +1 or -1. We are currently working on the implementation of network nodes with vertical connections because our diagrams force us to recover Boole's distinction between primary and secondary propositions, eliminated by Venn. Complex propositions of the type if P implies Q, then R implies S go beyond syllogism because they connecting nodes that are not naturally related by the elementary combination of characters. That is, the secondary propositions establish a posteriori connection between nodes that are not in the same network path. For example, we do this when we state that if there are students who work, then there are students who do not work. In our networks, it can be true at the same time that I have A and not A. If we want to operate with the same rules of the propositional calculus, we must establish that there can only be one true object node in the network. As you can see in the example, we have interpreted the disjunction with existential charge, but we could also have reached a hypothetical conclusion of the type. If there is P, then there is no R. In this case, all the non-removed nodes would remain yellow. In this Congress we present 4 papers based on our doctoral thesis. Marlow Logical Diagrams for Visual and Heterogeneous Reasoning. In the videos of paper 32 we can see the practical application of expectation networks in the classroom. In the videos of papers 4 and 21 we present some theoretical aspects of Marlow's diagrams, as well as their good results in the teaching of logic.